Hey guys, thanks for watching. In this video, we're going to be going over the Week 9 concepts for Physics 111. So here we're going to be covering circular motion, and to start off, we're just going to go through a couple different terms and notations we're going to want to familiarize ourselves with before we jump into the concept. So first off, arc length we're going to denote as a lowercase s, angle measure is going to be theta, angular speed will be a lowercase omega, and tangential or linear speed is going to be a lowercase v. So let's take a look at this image on the right, and this image is basically a diagram of our circular motion. So we can see we would start at a point A and end at point B. And here we see that delta S is basically the path we take to get from point A to point B. And we also see over here with this equation, in order to calculate delta S, we would take our radius and multiply by our change in theta, so our change in our angle measures. So we're going to take our final angle minus our initial angle, multiply by radius, and that'll give us our change in arc length. So next we see that our angular speed is going to be equal to our change in theta, or our change in the angle measure, over our change in time. And we also see that velocity is going to be equal to our change in our arc length over our change in time. So next let's talk about period versus frequency. Period we're going to denote with a capital T, and it's the time required for one complete revolution. So basically we could say that period equals time per revolution. Frequency is going to be denoted with a lowercase f, and it's the amount of revolutions per unit of time. So we can say frequency equals our revolutions per whatever unit of time we're using. And we can see the relationship between the two right here. We see that frequency is equal to 1 over period, and period is equal to 1 over frequency. And here we see we can also find our angular speed using 2 pi over our period, or multiplying by 2 pi times f, which is 1 over period, which is why that works. And then velocity can be found by taking the circumference over the period. So we have our equation for our circumference, 2 pi r over our period, or we can multiply 2 pi r by our frequency. Alright, so next let's go through what actually happens when we're making a turn. So we can see it in this image on the left. We have a blue car in a roundabout making a turn. So let's kind of analyze what's going on during that turn. So we see here we have a diagram of the turn, and basically we chose 2 points. We chose our initial point, which we're going to call point A, and our final point, point B. And we're going to analyze the different components of our motion during these 2 points. So we know that the path that we took between the 2 points is going to be delta S, or our change in our arc length. And let's look at our velocities first. So what's important to realize is that with circular motion, our velocity, or our linear speed, is always going to be in a direction that's tangent to our delta S, or our change in arc length. So at point A, we see that our velocity is facing in this direction, and then at point B, it's facing in this direction. So now let's think a little bit about acceleration. We know that acceleration is equal to our change in velocity over our change in time. And we know that our change in velocity is just our final velocity minus our initial velocity. So let's do some vector addition in order to see what our resultant would look like. And our resultant is going to be our change in velocity in this case. So we start off with our final velocity, which looks something like this. And then now we're going to want to subtract our initial velocity, but when we're doing vector addition, we don't really subtract. We're going to add basically the same magnitude of our initial velocity, but we're going to change its direction. So it's going to be a negative initial velocity. So basically it'll be something like this. But now we're going to make sure it points in the opposite direction. We're going to call this our negative initial velocity. So now we've basically subtracted our initial velocity from our final velocity, and we see that our resultant is going to be facing directly downward. So we know that this is actually our delta V, or our change in velocity. And at this point in the image, we found out that delta V is facing directly downward. And that's actually facing directly towards the center of our circle. And if we were to repeat this same process at different locations during this motion, we'd find out that in each case, our change in velocity is going to be facing wherever the center of our turn is. So what we can conclude from that is that if our acceleration is the change in velocity over change in time, and our change in direction is always towards the center, then our acceleration is also going to be facing the center. And we know that our force is going to be equal to our mass times our acceleration. We know that acceleration is a vector, so it has a direction. And we know that our force is also a vector. So therefore, if our acceleration is facing the center, our force also has to face the center. So this is just a really important thing to remember when we're dealing with circular motion, that all three of these things are going to always be facing the center. And what we can conclude is that in order to make a turn with a constant speed, a net force toward the center of the turn is required. And this net force toward the center of the turn is what we actually call centripetal force. And knowing these different relationships, we have two more equations which come in really handy. We have an equation to find our centripetal acceleration, which is going to be v squared over r, and we have one for centripetal force, which is going to be our mass times our centripetal acceleration, or our mass times our velocity squared over r. Alright, so next let's talk about centrifugal force. And right off the bat, we need to realize that this is a fictional force. So it's not really a force. It's just, we call it a centrifugal force. And we're going to explain what this actually is in a little bit. So let's look at this diagram with the merry-go-round. And let's think about actually sitting in the merry-go-round, or for instance, sitting in a car. When we're making a turn, we feel as though we're being pushed outward as we're making that turn. And that feeling of being pushed outward is what we call the centrifugal force, and we can see that here. However, this isn't a real force, it's fictional, and we know we have already defined that our force is always going to actually be facing towards the center of our motion when we're dealing with circular motion. So we know that this force isn't here, but why does it feel like we're being pushed outward? So basically what's going on here is we discussed earlier that our linear motion, or v, is always going to be tangent to the circle. So here's a couple different linear motion vectors. So basically what happens is when we're at this point, our linear motion is facing upward like I drew here. But then when we're over here, it's already going to be facing in this direction. So basically what we have here is we're constantly changing directions. And let's think back to Newton's first law, which is the law of inertia. And we know that a body in motion is going to tend to stay in that constant linear motion. So basically, since our linear motion is constantly changing due to inertia, we're always going to want to stay in whatever linear motion we were in. And because it's always changing, what happens is we have this, we're going to perceive this force pushing us outward, because basically our velocity or our linear motion is changing so much that it's just going to feel like we're being pushed outward. And we can see here actually in the image that the person wants to keep moving this way because of inertia, but we can't, because we're stuck in this circular motion here. And basically that's the idea behind using a centrifuge when we're separating blood samples, for instance. Because of the different densities within that sample, when we run the centrifuge, it's going to spin this sample at a really fast rate. And what's going to happen is the different densities are going to separate. Basically, they're using this false centrifugal force, this fictional force, in order to move the different densities of the components within that sample and separate the sample. And next we'll be talking about inertial versus non-inertial systems. So in an inertial system, it's going to require a frame of reference in which Newton's first law is valid. So the law of inertia has to be valid in this frame of reference for an inertial system. And then in a non-inertial system, it's a system in which one or more frictional forces are present. So basically all rotating systems are going to be non-inertial, and as we know, Earth is rotating, so basically we're within this non-inertial system because we do have these fictional forces like the centrifugal force present. Alright, let's take a minute to analyze this animation we have here. We have both a 3D view and a top view of this rotational system, and we can see that a blue figure is throwing this green ball towards the red figure. And we can also see that from their perspective, it's going to seem as though the ball is moving with this curved path. And we know that's not the case because when we throw an object, as soon as we let go, assuming that there's no other forces acting on that object, we're going to have motion that's going to be facing in a constant direction. So really the object is moving in a linear motion, however it seems to be curving, and the reason for this is what we call the coriolis effect, and basically the system around the object moving in a straight line is rotating. So to the objects within the system, or the figures in the system, it's going to seem as though the ball is rotating when in reality they are rotating. So in our last animation, we already went over the Coriolis effect, which is basically an object that's moving in a straight line within a rotational system, but seems to be moving in a curved line because the system is rotating. And we would have the same thing going on if we were to watch a missile being launched from the North Pole from outer space. If we were to look at this from outer space, it would seem as though the missile is moving with this curved motion, but really what's going on here is the missile is moving in a straight line. However, the earth or the ground underneath it is rotating. So by the time it gets to this point over here, that point actually becomes this point because the earth is constantly spinning in this direction. So it would seem from outer space as though the missile has a curved trajectory, but we know that this is actually due to the Coriolis effect. And similarly, the Earth spinning is actually what causes this spiral shape in hurricanes. So in the northern hemisphere, we're going to have hurricanes are going to be formed when we have air moving to these low pressure zones. And basically that air is going to want to move straight down into those low pressure zones. But because the Earth is constantly spinning in this counterclockwise direction, we're going to add this sort of spiral effect into our hurricane, and it's going to give us this shape. And in the southern hemisphere, it'll actually have the opposite shape, since from that perspective, it's going to be moving in the clockwise direction. Alright, that's all for this video, guys. Thanks for watching.